Putala, good morning to all of you. Today we had some delay somehow. Now we are in the class and welcome to Thermodynamics Semester 2 B1 Manufacturing and Mechanical. Today, hope now here only we have 26 students. By right there should be more. See whether more students can join. There may be some issues of connectivities and all, but try to join the class, Putha. That is very important. Yeah. Because this is a supportive sessions. So these supportive sessions are very important, and the value of these sessions you will see in the exams even. That's why. So joining the class is always very important. Yeah. So today, if we start from the, if we refer to our notes, okay, if we refer to our notes, so this balloon examples, we use this to learn a lot, and even some work transfers of this PV to the power n, okay, like expansions, constant pressure processes, constant volume processes. We have followed all these things, okay, and we came to know about the polytropic process as well. And also here you can see especially you have some idea about the n values. You have some ideas about the n values. So that's why you need to go through the notes separately. You have to go through the notes. So today I'm not going to discuss this because I'm going to start another new session. From the previous slides, okay. Of this PV to the power n equals constant. For constant temperature process, as I mentioned, isothermal, you can see n is 1. Okay, and also for adiabatic, reversible adiabatic, we call isentropic, n is gamma. Okay, n is gamma. Gamma is the Cp by Cv. Okay. So the anything in between 1 to gamma, there is a possibility of having n. Okay. So practical examples for compressors. Air compressors n is 1.3. With the also compressor with fan cooling n equals 1.2. Water cooled compressor n equals 1.1. Okay. So you can see different n values here. Different n values. What's the use of n? What's the use of n really? So if you see the expressions, if you see the expressions, you may notice that the expression of N, that is in the work transfer, okay, that is in the work transfer. In these expressions of N, you can see this W12 expression, okay. In this expression of N, you can see that N is here as P2V2 minus P1V1 divided by 1 minus N. So when N is smaller, W12 is bigger, okay. Okay, N is smaller, W12 is a bigger value. Yeah, a bigger value. So N has some limits. N can vary between 1 and gamma. Okay, N. N varies. This is the polytropic index between 1 and gamma. Okay, gamma is the Cp by Cv. Try to catch this. Yeah, between 1 and gamma. And W 12 here, you can see maximum. Okay, W12, you can see its maximum. Maximum when, okay, when N is equal to, yeah, sorry, yeah, we will see when the N is smaller, okay, yeah. So we will consider in this way. We will consider in this way. In the compressors, we need W12 minimum. Okay, that is what we need because the work input. For compressors, you need W12 minimum. Minimum. For expansion processes means for turbines. Okay, opposite of that, let's say turbines. Turbines, you need a maximum work output. Work output, okay. So for compressors, you need minimum work input. Okay, that's how it is. So, so for compressors, you need minimum work input. So that's how it is for turbines. We are taking work output, then that should be the maximum work output. Yeah, that is important. So gamma is a bigger value. Gamma is more than 1. Okay, if you think of gamma, if you think of gamma, gamma is bigger than 1. Gamma value. And always N between, not to say varies, N is between. N is between. So you have N, okay. So it's more than or equal to, greater than or equal to 1. Also n is less than gamma. Okay, later we will come to this again. You have to go through the notes. It is very important. You must go through notes. That is very important. Go through the notes. So that is, I leave that part to you so that we can have a better parallel working on the knowledge. Yeah. So compressors, you need minimum work input to get the compressor, and even bicycle tire, bicycle pump, yeah. So you must try with minimum effort. Yeah, same. Yeah, compressor, you need minimum input, but turbines, we need maximum. Even engines, we need maximum. Okay, engines. Let's say power stroke, we need maximum. Okay, so we need maximum power output. Yeah, that is very important. So compressors generally, when n equals 1, that is isothermal, as I mentioned to you. N equals 1, that is isothermal, you can see. Water-cooled air compressors means the compressor is trying to maintain the same temperature, of course not that much, but is quite closer. So you can see water-cooled N is 1.1. Okay, means the inside the compressor, the air being compressed, is trying to maintain the same temperature throughout the compression. Then this N is closer to 1. Air cooled, still not that maintaining closer to water cooled, but anyway, it's the compressed air is getting little bit stable temperature, so N equals 1.2. When stability is deviating further, that is 1.3. Okay, so it is something like this. Let me explain it. Let me explain it in this way.
Sir, we can't see the presentation.
Oh, okay, okay, yeah, yeah, okay. So this is the one I mentioned about the N value. Yeah, N is between 1 and gamma. Okay, N is between 1 and gamma. So it's a must for you to understand these things. Okay, not memorizing, not memorizing, but understanding. Yeah, some, of course, some piece of knowledge you have to have some memory based, and also you may have to have some understanding. But understanding is the important. So you have to look into the lectures, the Zoom sessions we are discussing, and at the same times, you should work with your notes I pass to you. That is very important. Yeah. Let's see. I'm going to, anyway, today I'm going to start a new session, but let me discuss this part first. Before going for the new session. It's a very new, very important sessions. Hope you can remember this. 1 to 2. So this is expansion, receiving some energy as heat transfer, and there is a work transfer, the work done. Okay, state 1 to 2. So your state 1 will be this. Okay, state 1 will be this, and the state 2 will be this. Okay, so it is okay to even to get the repeated discussion, that is okay. So your PV values at 1 and 2, something like, let's say, initially you may have the high pressures, okay, smaller volumes, okay. So initially your pressure is here. After expansion, your pressure drops, okay, the pressure drops. And the same way your volume, okay, initially smaller volume, of course, V, let's say V1, okay, V1, and this may change to this V2, okay, V2, so same way P1, okay, and P2, and the general, if we think of P and V, okay, intermediate, something like this. So this is an expansion, this is an expansion. If I draw from 1 to 2, so 1 and 2. Let me draw it better. One to 2. Okay, and I will draw one more now. Okay, I will draw one more. It's possible. Yes. one more here. And if I draw one more line, how shall we try to change this? I think good here. See, one more line here. Okay, one more. Okay, so here P1, V1. Okay, P1 and V1. Let's say this is a fixed point. And finally, this expands to V2. That's true, V2. But your pressure may be different. Let's see. Pressure may be different. So you have different N values. So that's a point. That's a point. Your N value. Okay. N value is different in this expansion. So if you think of the final of this, the limit of this, if you think of the limit of this, and there can be two limits like this, okay, and like this. Yeah, let's say this is a bit steep. Yeah. That's why. So this N variation as mentioned here, let me bring this text here. So N is between 1 to gamma. Okay, so that's a point. N is between 1 to gamma. N is between 1 to gamma. Yeah. So that is the limits. So this is a work done. Okay. Work done by the system means there is a real work output here. Okay, real work output. This is the real because this is a power stroke. And you can see real work output. And what's important is real work output W12, okay, real W12 work output. Okay, so I take the word W1 real. This is the W12 work output. So here, even if you need to put a direction for this, let me see, it's possible or not. See the end. So there is a beginning and end. Okay, so likewise, I think the best is to Draw a simple analogy. So you can see a direction of it. Okay, that's it. This is a power stroke, and real work output is here. Okay, this is a power stroke. Put it here. Yes, and this one W12 maximizing. Okay, maximizing is important. Let's say this fire from petrol, let's say this is from a petrol engine. So you are burning same amount of petrol, and if your output is more, means that is what we need, work output more, energy for the given energy input, more work output is better. Okay, means it's more efficient. So you can see the expression. If I take W12, carefully follow this pattern. Your W12 expression is here. Okay, that is minus. Okay, because this is towards minus, so outward it is plus. So let's say, let's take, I'm going to write the expression for you. I'm going to write the expression for you here. It is something like, let's say, P2 V2, P1 V1, or P2 V2, let's see, P2 V2 minus P1 V1 okay. So outward means, okay, divided by, I would write this as in minus 1. P1 V1, okay. Minus P2 V2 divided by in minus 1. So this is W12. This is W12. This is not the topic today I supposed to discuss, but let me do this. So this is very general. So different in values. So you have different in values. Okay. So different in values. So based on the different pressure values at 2, P2 is different, but P1, it's mechanically fixed, the V2. Okay, so the V2 is mechanically fixed, so your P2 change. Okay, same way V1 is mechanically fixed. Okay, and even if you have the right timing for the ignition, and if the fuel is there with the right amount of spraying or whatever, or the mixing with air, if the point, even point 1, state 1 can be something like fixed. V2 is fixed, but P2 is varying. That's why different P2 values you can see based on the different W12. W12. Okay. So if I put here maximum, because you can see the bigger area here. Okay, underneath you can see bigger area. Let me show you that as well. Hope you can remember this. So area under PVN, that provides the work, okay, work transfer, work output. Area under PVN, you can see it here. It's very nice. Okay, area under PVN. So you can see it. Okay, area under PVN is the work. Okay, so let me put it here somewhere. So this is PVN to the PV to the power n constant. That is a polytropic process here. Okay, as you see here. This is the process. This is the process. So area under PV to the power n equals constant. The bigger the area, the bigger the work transfer. So here the work done. So in power strokes, we need to maximize this. So maximum W12. Okay, this happens at n equals what? Gamma. Okay, even you can prove this. Okay, at n equals gamma. Okay, n equals gamma means the biggest n value. Okay, biggest. So n is between gamma and 1. The biggest n means the biggest n minus 1. Okay, sorry. Let's say, I have to check this again. Anyway, this is n equals gamma. Okay, n equals gamma. And minimum, okay, minimum W12 at n equals 1. At n equals 1. Okay, minimum at n equals 1. Okay, at n equals 1. This is 1. Okay, so the maximum W12 at n equals gamma. Okay, because even in P2 V2, you can see the P1 V1 to the power n is P2 V2 to the power n. So this is finally, even you can have some more simplified expressions, but this is the case. N equals gamma, highest work done. N equals 1 isothermal means most of the heat loosened to the environment to maintain the constant temperature. So finally you have very low work output, N equals 1. Okay, and here we call isothermal. Isothermal expansion. Okay, so isothermal expansion. So N equals gamma, we call it isentropic expansion. Okay, so in between, generally the reality lies here. Okay, so in between 1 to gamma, the reality, the actual case, lies in between gamma and 1. Okay, in between, anything in between. Okay, that's fine. So this is like this. Okay, and all are polytropic process, PV to the power n. Okay, so this is polytropic process. Okay, good. So this is for the power strokes. Okay, good. And in the text you can see gamma, the situation. So this explanation is about the compressors mostly. But in compression and expansion, if forms perform rapidly, means the speed is higher, and of course friction is lesser, okay, and if no heat goes out or no heat losing, so we call the adiabatic, okay, adiabatic, we call reversible adiabatic. It's not mentioned here, but isentropic means reversible adiabatic. So let me explain it later, okay. So it is like this. Okay. The same way, in this power stroke, I changed to compression. Okay, compression. So this final becomes 1, the bigger volume. The smaller volume becomes 2. Okay, W12, a work is done towards here. Okay, W12, a work is done towards. And of course, there can be a heat interaction. Okay, heat interaction. So I draw just over here. This is like this. So then this is a kind of a compression. See, the volume is getting reduced. So this is your P1, sorry, V1. Okay, and you may have a P1 value, P1. Okay, P1 and V1 is somewhat fixed. Okay, P1 and V1, quite interesting. So let's say this is the point. P1, V1. Your P2 can be changed, and yes, something like this. Nice. Arrow the other way. Easier. like this. Okay, your V2 is the same, but your P value you can see different. So work input for compressors. W12 minimizing is important because from small work we have to maximize it. It means the compression effect. Okay, and still this is the expression polytropic, the same. Okay, the same. Here it's a compression somehow. So state 1 to 2 becomes this. Okay, quite interesting. Quite interesting. Okay. I need to move this. V2 here. V is here. This is V1. Okay, this is V1. V2. Okay, P1. V1. Okay, I think enough. You can understand this very well. State 2 is here. So this is the V2 constant. that is mechanically fixed. So here, let's see. I need to rewrite. Let me rewrite afterward. Yeah. Let me rewrite this afterward. Yeah. Good. This is the minimum W1, minimum. Okay. Compression. This is the maximum. Oh, sorry. This is the maximum W1. This is the minimum W1. Compression. Compression. So anything in between like this. Okay. Hello. Hello. Okay. Good. So it's the same thing. Minimum W1. Maximum W12.
එහෙමනම් මිනිත්තු ගන්න 3000 2000 යන්නේ. ඒක ලයින් එක වගේ අදින්න ඕනේ. ඉතින් බාරේ යනවා ලයින්. මේ ලක්ෂයක් කියලා කිව්වේ. ඉතින් ඒ පැත්තට ගිහින් තියෙන්නේ. අපි ෆෝන් එක ගන්න ගත්තේ තියෙන දවස් වල 10. මේට වයර් එක නැති ඉඳලා අපිට ගන්න විදියන්නේ. අපේ නම් තියෙනවා. අපි සල්ලිත් දියලා තියෙන අපිට නෑ වයර්. කියලා ඒ කාලෙම පුංචි ඉවරයි. මේ යන කාලෙත් තියෙනවා. උදා තාන්තිලා ඉතින්.
පුතා කවුද කතා කරන්නේ? 22M17159. Please mute your mic, Puta. No, okay. Okay. Yeah. So the same way, you can see minimum W12, isothermal compression, maximum W12. Because again, it's the same. Okay, work done is under the curve, the PV area. So, okay. So I just keep it minimized. So W12 minimizing is important here. Okay, W12 minimizing is important. So compressors, we try for the compressors, let's say. Instead of compression stroke, let's say compressors. Compressor work. Compressor. So the work input, W12. Minimizing is important. So that's why minimizing means n equals 1. Okay, that is isothermal. Okay, that is isothermal. Isothermal. Okay, very important. So let's see what are the things here hidden. N is between 1 and gamma. Okay. For compressors W12 minimum input. Okay. For compressors W12 minimum input. Okay. At N equals 1. Okay. That is very important. Okay. At N equals 1. Anything more than 1. Yeah. So engines, I take this out. Okay. Because this is related to compression process. Right. Okay. So now you have some understanding, general understanding for power, stroke, okay, or the delivering of power, work output, yeah, maximizing is important. Then gamma is 1. Sorry, N is gamma. Okay, then N is gamma. Gamma. Okay, so here you can see it. Power stroke, we have to maximize, not the minimize the minimum work. So N equals 1 is not the good arrangement or a solution to get some work output. Okay, but for compression, for sure, we should try to maintain the compressed air almost at a stable temperatures. We should not let the temperatures rise. Okay, because rising temperature, because the compressing is mainly to make the molecule dense. Okay, compression is to make the molecule dense. Okay, yeah, to make the molecule dense. But when we try to put some effort to make the molecule dense, any heat into the compressor makes the molecules move very fast. So when you are dense, when you make the molecules dense in that system, and at the same time, if these molecules, if you can make the molecules silent, silent means you should let it dense at the same temperature. Practical aspect. Compressor air compressor air compress කරනකොට ඒ compressed air රස්නේ නම් මොකද වෙන්නේ? It's a resistance for the compression. අපිට නැත්නම් පුළුවන් තරම් මේ ස්පේස් එකේ තියෙන air quantity එක වැඩි කරගන්න. It is not about the pressure, but we have to have the pressurized highest quantity of air. දැන් මොකද වෙන්නේ? දැන් compress කරනකොට you will reach the pressure, but if the temperature is little high, මොකද වෙන්නේ? Your quantity of කියන්නේ හුලං වල තියෙන බර අඩුයි pressure එක තිබ්බට. හුලං රස්නේ නා. තේරුණා නේද? compressor එක ඇතුලේ කියන්නේ compress වෙච්ච හුලං වල බර අඩුයි ඒ හුලං රස්නේ නා. හරි නේද? උඩ ඒ හුලං වල රස්නේ නැත්තම් සීතල නම් ඒ හුලං වල බර වැඩි එකම ප්‍රෙෂර් එකට. ඒකයි දැන් compress කරනකොට so you may experience some raising of temperature. Temperature එක උෂ්ණත්වය නගින්න බලනවා. So we will try to remove that energy by cooling the air. ඒකයි compressed air වලට there can be fins or even there can be heat exchangers to remove the warmness or the hotness of air being compressed. Okay, making the air cooled down, yeah. Okay, better than nothing, but better than nothing. But water cooled is better than air cooled. මොකද ගොඩක් රස්නේ හුලං වල තියෙන එක ගන්න පුළුවන් compressed හුලං. So N is reducing. Initially N is for compressors here you can see. Air cooled N is 1.2. Water cooled N is 1.1. No air cooling or water cooling N is 1.3. 1.4 means it is gamma. N වල value එක බලන්න 1.4 is gamma. එතකොට compressors වල මේකයි. එතකොට engine එකක ගත්තාම it's other way. If the engine is too cold, you will not get the sufficient efficiency or the work output or the power output. So engine, it is different, compressor is different to compressor. Okay, so you have to have a natural understanding first, and then you may understand this theoretical knowledge in a better way. Okay, with no natural understanding, this knowledge may not be that complete. Making natural aspect එක බලන්න. Okay, natural aspects. So for compressors, minimum W1, that is important. Okay, yeah. When you compress, yeah, minimum W1. That's why if you know the art of compression, you can come out with very good design solutions, no matter compressors, no matter engines. Okay. Any question? Any question? Any question? Let's see. Now we have 37 students. Very good. So you have some little work. One thing is you have to go through this the notes given to you. It's a complete note. Okay, so you have to go through the notes, and you have to, because looking at the note, it is very difficult to get some practical sense. So the practical sense is number one, followed by the notes, your knowledge will be completed. So we can do text හැම දෙයකම තියෙන ප්‍රායෝගික පැත්ත තමයි තේරුම් අරගෙන තියෙන්න ඕනේ පුතා. තේරුණානේ ප්‍රායෝගික පැත්ත. අන්න ඒක දන්න තරමට තමයි ඔක ටෙක්ස්ට් එක තේරෙන්නේ. නැත්නම් you may have only some equations. ඒකයි. තේරුණානේ? Try to understand this and if I make a summary, this is the expansion means the power, releasing power. So I just put power stroke because piston cylinder here. So W12 is the work output. That's the area under the PV curve here. The function is PV to the power n constant. So area under PV. So maximum, having maximum area under PV means that is the maximum work done. Okay. If the PV curve running like very low, at very low level, your work done is very less. Okay, but we need the high work done here, higher work, higher area under PV. So in the higher work done, this n has a value of gamma. That's the maximum limit. Okay, the minimum work done n is 1. So we know when n is 1, PV equals constant means it's a constant temperature process. We call isothermal. So isentropic and isothermal. In between expansion, anything can be for n. Okay, n is between gamma and 1. Okay, so the very good engines, they try to maintain this isentropic nature of expansion. Okay, isentropic nature of expansion is very important for the engine's power, and also even for the compression engines, there is a compression stroke. So if the compression stroke somehow can be isothermal, it is much better. But making the compression stroke isothermal and making the power stroke isentropic, that is ideal, and there may be possibilities somehow. There may be possibilities. Okay, near isentropic and near isothermal. You cannot say exactly isentropic power strokes or expansions. You cannot have the isothermal compressions, but near isothermal compressions possible, near isothermal expansions possible. Okay, so this for the compressions. The other way, you have a bigger volume and smaller pressure. You are reducing the volume from V1 to V2 here. Okay, you are reducing the volume from V1 to V2. V1 is here. Yeah. Then pressure rises from P1 to P2. Quite understandable. Okay, quite understandable. And then again, you can see different n values possible. Different n values. So n, if n is gamma, you have the, you need the highest, okay, work input. Okay, same way when n is 1, those are the upper and lower limits. You need the lowest work input to get the air compressed. So for compression wise, lowest is important. So n equals 1 is important for, how to say, it's important for compressions, air compressions or gas compressions. Okay, so unlike work done or expansions, n equals gamma is more desirable. Okay, so n equals 1 or near isothermal at least. Okay, yeah. So n equals 1. Near isothermal means not 1 but close to 1 maybe. Okay, but for the expansions, n equals gamma. Okay, n equals gamma. So near isentropic, at least near isentropic. Okay, nearly isentropic is good. Yeah. Isentropic means a reversible and adiabatic bond. So we will understand that also afterward. Isentropic expansions, there should no heat goes out as losses. I think I have shared with you earlier isentropic expansion. So this is something like very much insulated. And also this work, the energy there with this combustion, the energy, no releasing of that thermal energy as heat loss. And also this should purely do a work so that if the friction is negligible, that is practically very important to get the pure 100%, means the maximum possible work done with minimum possible losing of the thermal energy availability. So that's what we call the isentropic. Huh? Yeah. I think you know this. In the class we have discussed. So very nice, very good 2 slides. And the earlier knowing of this, consider good. Okay, consider good. So if I try to rearrange this, maximum working, I will put it here. Maximum. Okay. PVN, I will put it here. The minimum working is here. Okay. The reality is in between. Anything can be. Okay. Yes. Somewhat. Okay, somewhat okay. Good. Yeah. So let me save this. So this understanding is very important. Eh? Sometimes you have some unknown knowledge, but later you should learn this. But this gamma and all, yeah, even I have mentioned this to you. Later we are going to learn this. Eh? Good. Yeah, okay, good. Okay. Okay. Now can you look into your thermodynamics notes? Okay. This is about perfect gases. Okay, perfect gases. You have to understand this. Okay, perfect gases. Because when it comes to this working fluid, so yeah, gas, steam, refrigerant. So there can be variations. So understanding what happens. Having a good sense about perfect gas is very important. Okay, so I just put it here, but please take note that you have to explore. Okay, you are exploring this perfect gases. You are exploring. Yeah? That is your tasks. Yeah. So you supposed to explore. Okay. You supposed to explore. Yeah. Let me try to make it better. What is this? Yeah. So you supposed to explore this perfect gases. Even in some past papers, I put perfect gas based questions. Okay, so having a good knowledge about perfect gas is important. Yeah, so same like you know the working fluids, steam. Okay, then the compressed air. Okay, compressed air. Also the combusted air that is in the engines and all. Yeah, combusted air and air or gas. Let's see. We call air or gas. Sometimes we may be using the natural gas and all. Yeah. So air gas system, right? Yeah. So same way, some cases may be refrigerants. Learn what refrigerant means. Working fluids in cooling systems. Okay. And here under this, so we have to learn perfect gas. Perfect. Okay. Perfect gas. We are learning about this because these all are falling under working fluids. Okay. In both closed systems and in open systems. So steady flow, let's say, open systems means steady flow systems. Okay, that's why working fluids. So we have learned about steam a little, compressed air a little, this because PV to the power n, yeah, and perfect gases. Give me a second. So steam, you have to look into steam tables. Refrigerants, you have to look into property tables. Okay. So steams, you have to look into steam tables. Refer steam tables. Yeah. Okay. Steam, you should refer steam tables. There you can know more about this. Refrigerants, again, property tables. Tables and graphs. Okay. Property tables and graphs. Not to say graphs, charts. 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 Yes. Okay. For compressed air, combusted air, gas, all. Okay. So for this too, so we consider ideal gas nature. Ideal gas knowledge is important. Okay, ideal gas knowledge. Yeah. Behavior of ideal gas. Yeah. Ideal gas behavior. We should know. Ideal means, not to say ideal, this is real gas behaviors, okay? Real gas behavior is important. Combusted air or gas, again, the real gas behavior is important. Okay. Refrigerants, it's okay, we can look into property tables. But sometimes for high pressure, high temperature gases, we are still looking into the gas behaviors. But anyway, for compressed air, real gas behaviors. Combusted air gas, real gas behaviors, okay. And why you need perfect gas knowledge? Perfect means ideal gas. Yes. Yes.
So your mic is muted.
Thank you very much for reminding. So the perfect or ideal situation of gases, we have to understand that, because even some real gases we can look as perfect or as in perfect or ideal situations. Okay, in perfect or ideal situation. Ideal situation. So one aspect of this ideal situation is we call perfectly elastic nature collisions, nature of collision between molecules. Perfectly elastic nature. Imagine සමහර වෙලාවට rubber band එකක් වගේ එකක් නිකන් බරක් එල්ලලා අදින්න ඇදලා release it. You take a rubber band or an elastic, hang one end and the other end you tie a mass and pull the elastic and let it move. If it is perfectly elastic and if there is no any wind resistances, this back and forth or up and down movements is not stoppable, and naturally it will be oscillating up and down forever. We call this perfectly elastic, means the energy of that system remains within the system with no losing to the surrounding. ඒ කියන්නේ ඒක එනර්ජි එක lost වෙන්නේ. ඒක elastic කියන්නේ. එනර්ජි එක transfer වුණාට එනර්ජි එක lost වෙන්නේ. දැන් මෙතන ගත්තාම for these molecules. So when the molecules hit each other, but the molecules energy levels remains. That is the one, the elastic nature, the perfect elastic nature. Even the molecule hit a wall and bounce back with the same level of kinetic energy. So for that reason, there should be no bondage between molecules. No bondage. Molecules means no bonds. Because between molecules, of course, to form the molecules more than one atoms. Okay. So here no bondage between molecules, because there are some, there can be example, water remains together, even water remains as clouds. One thing is because in between water molecules, there is a kind of bondages. Okay. In between the molecules. Okay. So those are bipolar bonds. Somehow there are bonds. So for ideal nature, there are no bondages. Okay. No bondages means, so in chemistry terms, no bonds. Okay. In between molecules. So no bonds, so attractions. So bonds means attractions or repulsions, both are. Let's see. Okay, attractions or repulsions. Okay, yeah. Among molecules, let's say between means the two molecules, no attraction, repulsion. For many also it's the same. So this is the perfect nature. Okay, perfect nature. And this is nothing to do with the molecular size. Okay, so nothing to do with the molecular size. Means molecular size is not important for this perfect and ideal nature or situation. Nothing to do with molecule size. Yeah. But of course, the heavier ones, it is very difficult to achieve the ideal nature, but the lighter ones, nothing to do with the molecular sizes. So we are considering that, but here let's see, I take this out anyway. So basically this is the ideal situation. Okay, this is the ideal situation. So let's say, so if we take real gases, listen well, Buddha. Let's say real gases, helium. You have seen the animations. Yeah. This helium animation, the speed is 2 trillion times slower. 2 trillion billion 1000කටත් වැඩිය billion 2000කටත් වැඩිය speed එක අඩුයි. Billion 2000 times වලට if you take this speed multiplied by 2000 billion, you will see the actual speed. Having this, the reason is molecules, there is no way of slowing down because energy, kinetic energy levels of the molecules remains the same. The reason is no bonds. Yeah. Okay. And for maybe lighter molecules, so the when the energy received by these molecules, speeds can be more. Yeah. Hydrogen molecules, H2 I put. Let's say hydrogen, yeah, here, hydrogen H2. Consider perfect gas. How about air, dry air? Instead of that, let's see oxygen. You can consider oxygen is, it has some closeness to this. Okay, real gases this are not ideal. And then nitrogen, little bit heavier. Nitrogen is bit heavier molecules. Molecules, the heaviness, you can check the heaviness, relative heaviness of the molecules. Even helium, I put He may be okay. Helium. Yeah. So hydrogen. So this is the natural state, because single hydrogen molecules will not exist. Yeah. Okay. So hydrogen, nitrogen also. Molecular forms, not in atomic forms. The natural states are like this. Helium, but only single. Yeah, only helium will say that. One single atom can be alone. Hydrogen, you need two together. Oxygen, two together. Nitrogen, two together. Okay. Likewise, ozone, three together, but this can be a special arrangements. This is ozone. Ozone has, because ozone layer and all, you know. Yeah. So ozone. So in the higher levels of atmosphere, you will see ozone. Yeah. It's rare experience to us. Carbon monoxide, carbon and oxygen together, it remains as gas. Okay. Also can be carbon dioxide. Okay, these are the gases. Okay. Yeah, there can be many such gases. Huh? Carbon monoxide is not that stable. That's why carbon monoxide is toxic, because carbon monoxide is not stable. Even ozone is not stable, means not good for human health. Okay, CO not stable, but there can be carbon monoxide. So there can be many, let's say, nitrous oxides and all. So let's say burning nitrogen, we call NOx. Burning sulfur, SOx, sulfur oxides. X means any number can be, so NOx and SOx. Anyway, I take this two out. Yeah. So how about the water? How about this? Putting under gases, is it possible? Water putting as gases, do you think it's possible? Why not? Let's say H2O, not water, H2O. H2O. High pressure. Okay, high pressure, not to say high pressure. Let's say low pressure. Low pressure and higher temperatures. Because higher temperatures makes H2O molecules violent. Okay, so that they can have more speeds that they may not have this significant intermolecular attractions. Low pressures, that's why you can see in a drying process, drying කියන්නේ වේලන්නේ. පුතා අහලා තියෙනවද vacuum drying කියලා? Vacuum drying. Vacuum drying කියන්නේ, so you vacuum, example vegetable, if you need to pack vacuum packing or vacuum drying possible. So you subject this vegetables or whatever into low pressure so that these molecules are quite loose and their interactions, and they are free to move and leave even. So low pressure and high temperature. Yeah. Even there are applications in some systems you can see. To remove moisture, sometimes people use the vacuuming or operate vacuum pumps to remove moisture sometimes, to maintain very low pressure so that this moisture is in very free molecular forms. Okay. So even H2O possible. So real gases. So low pressure means, I would say, negative. Okay. Means a vacuum level. Negative pressures. Now you can see. Anyway, I take the negative pressure out. Low pressure. Okay. Low or negative pressure. Negative means below atmospheric, vacuum levels. Yeah, negative pressure. and high temperature. Even these gases, high temperature, yeah. So those are like gases. H2O can be like a real gas, okay? Real gases, H2O. Okay, low negative pressure and high temperatures. Water also has a gas behaviors. Okay, H2O like, yeah. And ideal gas behaviors, let's say this gases, real, again at low pressure and high temperature. At low, so I take the negative, because not necessary to be negative, because these are even at atmospheric pressures, those are really in gaseous forms. So higher temperature is enough even. Yeah. Low pressure is also okay to put. Even you can see the natural gases. I put Ng, natural gases. Hydrocarbons example, propane, butane, heptane, pentane, methane, ethane, those are the hydrocarbon gases. Okay, hydrocarbons. Even in your gas cylinder, at home, if you are using cooking gas, cylinder, all you can see in liquid form. Why? High pressure. See, gas turns into liquid at high pressure. And if you, and also at low temperature, for that pressure, it is not high temperature. So it's turned into liquid, high pressure. Yeah. So when you open the regulator or when you on the gas cooker, pressure drops suddenly. Means it's a low pressure for that high pressure liquid. Turns to low pressure, immediately turns into gas forms. Okay. And if the temperature is further high in the burners, yeah, it is really most of the time like the ideal gas nature. It will come to the ideal gas nature. Okay. So high pressure, sorry, low pressure, ideal gas behaviors of gases. You can see these gases and even the natural gases. Ng or hydrocarbons. I put hydrocarbons. Gases like methane, ethane, propane, butane, pentane, all the things, the lighter ones. Even pentane is not in the gases. Pentane, even petrol is pentane. Yeah. Okay. Petrol also hydrocarbon. Let's say you can Google what's a hydrocarbon, name of petrol. you will find it pentane. So ethane, ethane, propane, butane, until butane is okay. Pentane, normal pressure temperatures, you can keep it in liquid form as long as you keep the lid closed. You can petrol කියන එකක් භාජනයක තිබ්බත් මූඩිය වහලා තියන්න ඕනේ. So it forms little vapor there inside that bottle, and anyway it maintains certain higher level of liquids. That is the petrol හැටියට liquid form එකකින් තියාගන්න පුළුවන්, but you have to keep the lid closed. එහෙම නැත්නම් it all evaporated, and finally you will not see petrol, all escapes. Yeah, that's why. So it is in liquid form, but can easily be turned into vapor form even under normal ambient conditions. So you petrol station එකක petrol ගඳ because can easily evaporate. Oh, it's in the borderline of getting into gaseous form. Yeah. So ideal gases behavior, ideal gas behavior of the real gases. Simple, low pressure and high temperature. That's it. So depends on the situations. Even oxygen you can use as you can consider as ideal or the perfect situation of gases. Okay, ideal behaviors when the temperature is higher or pressure is lower. Atmospheric upper levels of atmosphere pressure is very low. All the gases they are having some ideal behaviors. Ideal behaviors. That's how. Even clouds at higher levels of atmosphere, water evaporates and somehow moves up and up at higher levels. Somehow, of course, it's at the lower zone of the atmosphere, but you can see because of that low pressure. Okay, it can be suspended in the air. It can because it's in the gas form. Yeah. And somehow because of the water, the molecular bonds all are together, so we see white in color because that is because of the passing of sunlight through that. We see white in color. Otherwise, if you really go near a cloud, sometimes may not be. That is anyway. That is because of the light effect. I think if not, you may not see the cloud even. Light effects. As I feel. Yeah. So anyway, it is something like inner gas behaviors. So ideal gases. Now you know that any real gas can be in the situations of ideal gases. Depends on the pressures and temperatures. So even in the piston cylinder, after combustion, power stroke, so your pressure is high. That is negative for the ideal behavior, but your temperature is more higher. Not to say more higher, but temperature also significantly higher. Let's say 400-500 degrees Celsius. I don't know, we have to check it. I cannot remember. So higher degrees somehow. So you have a pretty good gas behaviors, energized gas. So that can be ideal nature. So even the ideal gas. So perfect ideal gas, there is an equation. pressure times volumes is equal to A number of molecules. There is a constant and temperature. Okay, this is ideal gas equation. Okay, we call this ideal gas equation. Ideal gases, you will see this behavior. So we call this ideal gas equation. Okay, ideal gas equations. Is possible, ideal gas equations we can use. So there are a lot of analysis we can do with this knowledge of ideal or the perfect gas equation. Okay, ideal or perfect. Okay. Okay, I believe you can understand this. So you go through your notes and see whether you can get this knowledge about the perfect gases. So I need the slides. Give this as 3 slides. One is here, the other one is this one. This is this. Okay. So PV equals nRT. Understand this PV equals nRT. This is this is very important. Okay. Understanding PV equals nRT. You have to understand this. Okay. Not remembering, understanding. Okay. So what is this? You have to understand this. Okay. It's very important for you to understand. So then you have this work done equations and all. Let's see. You have learned about this, and with your understanding, okay, with your understanding, you can combine that work done knowledge, okay, work done knowledge together with this PV equals nRT expression. Okay, this can be the second slide. So you can connect this. Okay. You can connect this to this applications. If you have understanding, so that is the importance. You can see the connection. Okay. Same way for the engines like power strokes performing work outputs. Okay. Not receiving like compressions, but here the work transferring out, really out. Also, you can use this connection. This is very important. So this is something like a guideline for you. Okay. So with this understanding, you can use this. Yeah. That's why. So understanding PV equals nRT is what important. Okay. PV equals nRT. Tala, since the keyboard, did it make sense for you? And as moving further, with this understanding, you can look into this equation as well. Okay. This is a single name. Another equation there, we name it Van der Waals equation. A little deviation from this. When you understand PV equals nRT, you can use the improvement of that for using in actual gases, means with bonds. That's other knowledge, okay? That's other knowledge. So okay, I will do this way. Using on this, and then by the side. This van der Waals equation, okay? Thinking of doing this in a nice, as a nice slide. Let me try. Took a bit time, that's true. Yeah, okay. So you can use van der Waals equation as well. Give me a second. So after understanding PV equals nRT, you can learn about van der Waals equation as well. And then you can see the connectivity of these two. Okay, connectivity of these two. And then also using this van der Waals equation in these applications, then you are done. Okay, so this mind map says a lot of things. Of course, this is based on understanding PV equals nRT. Okay, you can look into this as well. Okay, and also we have one more. Let me put it. Another form of this is PV equals MRT. Okay, you have to learn this as well. Okay, quite interesting. So I leave this to you, but I did a lot of background preparations about the ideal gas. Okay, and this is quite nice. PV equals nRT knowledge, and let me put the other one also. PV equals MRT. m times r times t. Okay. Good. Very good. So this is important. Okay. So this is a bigger level of understanding. This is very important. And if you know this part very well, I would say yeah, good. So can you do this? You know about the polytropic functions and also the for compression and expansion and also constant volume processes, constant pressure processes. You know all the things, and these gases can be considered as working fluids. Then understand this nature of gases by knowing this PV equals nRT and PV equals mRT. Okay, that's a big difference. Even if you see some similarities, yeah. The difference you can see in N and M and this R's. Okay, so let's say this is R. UT. Okay, RUT. And here, let me put R. ST at the moment. So I prefer to do this way. This R is RU. Okay, that's the situation. Here I put this R as RS. And I keep it in RT and MRT. These R's are different, okay? NRTR and MRTR. In NRTR and MRTR different. That's why I put here. For this case, NRT, R is RU, and MRTR will put R is RS. Okay. Some more clear. Yeah. Okay. Good. Yeah, nicely done. Okay. Yeah. Good. So this is your homework. Okay. You at least try to do this. So I believe you can note down this, and I will email you this 2D presentation as well. Okay. Because after that, we are going to look into some more advanced analysis, application-oriented analysis. Okay. So here the natural understanding is very important. Understand doesn't mean that, let's say someone can say PV equals nRT, P is this, V is this, N is this, R is this, T is this. These are the units of this. That is not enough. It's not the understanding. Okay. So that's why I did this preparation for you. Make sure you understand this. Okay, good. Today topic, I prefer to keep this as the topic today. Okay. Now, so any more questions before proceeding? Yeah, it is 12 o'clock anyway. Any more questions, Putta, before proceeding? Any more questions? Any more questions? Okay. So, yes. Any more questions? Puttanaට කියපු ටික තේරුණාද? Okay. Another section I'm going to start. Okay, but this is again the background preparation. So this is about the background preparation. Let's see, since we have to start from simple. සමහර වෙලාවට ඔය ප්‍රොජෙක්ට් සීන් බිල්ඩින්ග් හදන්න අරවට මේවට කඳු කපන්නේ පස් අයින් කරන්න earth. Okay, earth removing. Let's say removing means removing. Okay, project. Okay, earth removing project. Let's say imagine that so this project, earth removing project. So let's see, if you have a mountain of earth, I can fill this. Yeah, very nice. Okay. It is slanting mountain of earth. And you are going to build, let's say, high-rise building. Okay, high-rise building. So high-rise building, let me see. This is the building.
சம்மாந்துறையில் ஒரு ஆள் கொரோனால உயிரிழந்துக்கிறாங்க.
சம்மாந்துறை அவரு பிறக்குமானதுல வந்தால் எங்க இருந்து வந்தவர்? அது ஆப்பர்ல இருந்து வந்தவரா?
என்ன சம்மாந்துறை 80 வயசு.
Arshad, Putta, can you be little mute your? This is the earth moving side, earth moving to build this building. Okay, so this building is in your mind. So you're going to build this. Okay. So this is in your mind. So you are going to build this. This is the site. So when we supposed to remove, we have to remove some earth here to construct this. Let's say you are constructing it here. Okay, this may be your construction place. So you have to remove some earth for sure. Okay, let's say you are removing some earth. You are removing this earth. So this is a big project. Okay, so you have to remove this. You have to remove this. So this is the earth moving project. Huh? Yeah. So put this building. This is in your mind. Put this building here. To realize this. Okay. To realize this. You have to remove a huge quantity of earth here. Okay. You have to remove this. Remove. You have to move this earth. Yeah, so I will take this removing. I will put this. So you have to remove this. So this is too early to put here. Okay. So to build this one, you have to remove the earth. So this is your project. Remove this part out. Move this part out. Okay. So you have to plan this project. So how are you going to plan this? Okay. How are you going to plan this? How are you going to do this? Okay. So this is what you have to do. This is your plan. Okay. This is your plan. So how you are going to do this, Buddha? How you are going to do this? The resources I put here. You may have questioned that why we are doing this for thermodynamics. Okay? Resources. What are the resources you need? Let's say the excavators. You need to excavate the earth, okay? And backhoes, okay? Spelling looks correct. Excavators, backhoes. Maybe this one, right? I don't know. Yeah, backhoes. Based on the size of this. Yeah. So what else? You may need dump trucks to load, okay, and unload this dump trucks. Resources, these are the things: excavators, backhoes, dump trucks. And of course, you need some, let's say, fuel sources, petrol or diesel, to run these machines, okay? To run these machines, you need energy sources as well. But for resources, I put this 3 only, and you need the operators as well, okay? So, and the other thing is excavators, backhoes, and dump trucks. So you are going to use this in cyclic way, or you are using one dump truck, dump the earth, and went back, and are you taking a new one? No, you are repeatedly using this. Using this resources, okay? Repeatedly means the or continuously. Using these resources, so you are reusing it again and again, continuously, okay? You are using this repeatedly or continuously, using these resources. So this is the point here, because otherwise you have to have a very costly operation if you are taking trucks for each and every removal of this earth in batches. So that's why. So you have to have excavators, backhoes, dump trucks. These are the resources. Okay. And one more. Unlike previous, you cannot simply, you can remove, but you have to put this earth somewhere in a suitable place. Means you have to look for earth dumping site. This is essential. Earth dumping site. Okay. Why? To unload what? The truckloads of earth. Okay, earth removed from the construction site. Okay. So you have to have the earth dumping site, a suitable earth dumping site. A suitable one. Okay. So earth dumping site also consider important. Resources also consider important. Of course, there can be operators and there can be some supervisors to manage the operations and all, but this is essential. Yeah. So these are the things, resources. And then you have to plan the, of course, the first should be the strategy of removing this project. So strategies should come first. Strategizing or planning and planning. Planning, this is very important because when you use resources, planning resources and all, it is very important to use the resources in very optimal ways so that you are not wasting or maybe not over consuming the resources. Yeah. Okay, so you have to plan this very well. You have to plan this very well. You have to strategize the operations. Okay, very important. Then, so once you strategize and planning, you know the quantity you need to remove, you know the space of the landing or the earth dumping site, the size, the matching with the earth removing quantities, and you know how many trucks and excavators you need, the optimal ones, because you cannot use only one. So it takes years because there is a timeline. You cannot use two because even it takes, if it is years, it is still two, using two dump trucks maybe still needs years. But let's see, if you are using 500 dump trucks, your cost may be very heavy and it may be a matter of several weeks, but the cost is very heavy hiring many dump trucks. Let's say you're buying this one, so it's a loss for you. So you have to plan the optimal resources. even dump trucks. You have to match with the excavators and the backhoes. You need to match all the resources. So matching is important, resources matching. Because if you take dump trucks and if you have very less backhoes and this excavators, dump trucks have to wait. Idling time is too long and it's a loss. Means always dump trucks should be in the move. Excavators should be continuously operated. Backhoes should continuously operated. Right? And the dumping site also in a with the proper space, it should be always getting filled. And the construction site, the earth is continuously getting removed. So there is a kind of a steady operation. The steadiness also important. Okay, resource matching and the steady operations, that is very important. Very important. Okay. Extremely important for this case. Good. So, any question, Putala? So far, any question? So far. Can you plan this? Can you plan this well? So for next week discussion, you have to plan this earth moving project very well. So I give some hints and all. So this is one of the parts. So you have to plan this well, and also you have to understand PV equals nRT also very well, and PV equals mRT also. Give me a second, Putha. Yeah, Putha. So I will be sending this file to you today, because without this it may be tough to have this, because there are a lot of background preparations. So let me save this as a PDF. So you know what to do. Understanding this and also understanding the earth moving project. Okay, understand the earth moving project. That is very important, and let me explain you why this is important in the coming session. So this is considered greatly important. Okay, put the message sent. Hopefully you will get it. That's all for today. So think about this and try to work something out, because if you can think about this, this will be very helpful for the next week. Not only for next week, this will be very helpful even for your innovations and all. Okay, yeah, for a very good thermodynamics knowledge, this will be very helpful for natural understanding. So please take this seriously and do this. And today attendance, we can see only 27, including myself. So anyway, it is very important to attend to the class, Puta. Very important, because you will not get this from books. That's why. So you should come to the sessions. It's a matter of just paying your attention, and you will receive the knowledge naturally. That's why. So one time done, even if you take the notes and you are going to read this, it won't that work effectively. That's why. So it is extremely important. It is extremely important you are joining the class. Yeah, I think you will feel it. So that's all, Putala, for today. Sorry for the delay. We got 30 minutes delay somehow due to some signal issues and all. But anyway, 3 hours we spent. Hopefully have received something useful and something different knowledge. Yeah, because standard knowledge you can look for everywhere. Yeah, I don't mind. And you have the textbook, the notes I passed to you. So please go through this and try to develop a very good, how to say, natural familiarity and understanding of the subject. බොහොම ස්වභාවික දැනුමක් සහ තේරුම් ගැනීමක් තියෙන්න ඕන. තේරුණා නේද? That is extremely important. ඒක මත තමයි පුතා ඉතුරු ටික යන්නේ. හරි නේද? හරි. Okay, Buddha, then that's all. So let me stop the class. You take care, all of you. So anyway, it's a duty for you to learn the subject. It's a big duty because you cannot stop learning. Because you are the future. You are the future of the country. So you cannot be idling. Yeah, you cannot be idling. So there are a lot of things to explore. As subjects, even in the nature, you have to explore a lot of things. In the life, you have to explore a lot of things. And try to have some very good, wise behaviors these days. Don't think about the restriction of the mobilities. Of course, at this age. You know that getting along with friends and all would be much interesting, but these are restricted, and take this advantage to live with yourself, yeah, and also to live with family and to learn something for life, even life and beyond. Okay, and this subject really will help you to have some good philosophies and to have some good thinking approach, and also to have some very good learning skills. This subject is very important, and the students who are really on this know how important these sessions are. Thank you, Bhutana. So let me stop the class. Take care. Bye then. Bye. Bye.
Thank you, sir.
Okay, bye.